Hi all, back for another round of physics, and yeah, let's go at it. Last example problem for you, dealing with momentum, and we'll probably, next video, go off into rotational motion. So yeah, here we go. So up in front of you, a neon atom, 20 atomic mass units, makes a perfectly elastic collision with another atom at rest. After the impact, the neon atom travels at an angle of theta from its original direction, and the unknown atom travels away at phi. What is the mass in atomic mass units of the unknown atom? Rock and roll. Okay, so this is actually, if we see, we actually have a 2D collision now, because notice we keep getting these angles. So that kind of indicates to us that we're dealing with some sort of 2D collision. And then, of course, we have this hint that the collision is perfectly elastic. Okay? So it's always good to draw a picture. I, of course, have cheated and have drawn one in advance. And this is what we're dealing with. Neon atom comes in, strikes the unknown atom, come off at angles. And we have three ideas, well, two ideas that we're going to use here. One, we have momentum. And I said three ideas because here we have 2D. So there's our second idea, that it's in 2D instead of 1D. And of course, the second idea that we're going to have to use is the idea that it's elastic. In other words, that the change in kinetic energy is zero. Okay. Well, gird your loins. Here we go. Let's rock and roll. So I'm going to start with the, let's start with the x direction. X direction. And go ahead, take a minute, write down the equation. And I'll go for it myself. We have P naught, the initial momentum, is equal to the final momentum. Okay. Well, the initial momentum is just what I'll call here, I'll call it the initial, and I'll just use N to represent the neon atom. And I'm just going to leave it in terms of this. Okay, I'm going to leave it in terms of momentum, and hopefully you'll see why in a minute here. Sometimes it's easier just leave it like this. So if I set equals to, well, finally, I have the momentum of the final momentum of the neon cosine of theta plus the momentum final of the unknown particle, which I'll leave as question mark, cosine of phi. Yeah. You'll notice I have two unknowns here, right? I have those two momenta. Let's go ahead. Let's go for the y direction. Okay, you got it. Say P naught equals P final. Right. And here, the initial momentum in the y direction is 0, so I get to put in 0 here. And that will be equal to, and again, the final momentum of the neon. Here, instead of cosine, I need to use sine of theta, number 1. And second of all, we notice that the momentum of the unknown particle is moving in the negative y direction. So I better put a negative sign there. P final, question mark, sine of phi. Boom. We're 2/3 of the way through the physics already. Okay. So what I'll do, let's go ahead. Let's hang on to this one. Not writing all over it. Let's hang on to that one. So we'll move that down here. There's my x1. Here's the one from my y. Let's get rid of everything there. Excuse me. Well, now last but not least, we have to deal with our kinetic energy. We're going to use the idea that our change in kinetic energy is equal to 0. Okay? Now here's where I'll be a little bit sneaky. Okay? You remember the kinetic energy is 1/2 mv squared. V squared. And the question I have for you is, can you come up with a way of, instead of expressing this in terms of mass and velocity, can you think of a way of expressing this in terms of momentum? You got it? Good. Here we go. Well, instead, of course, the sneaky trick is to multiply by 1. So I'll multiply both top and bottom by 1. M squared V squared over M. And then you see, okay, well, that just equals, up here, I have P squared, the momentum squared. And in the denominator, I have 2M. Okay. So this is actually the expression I'm going to use for expressing my kinetic energy. Okay. And I did that because you notice the other two equations that I've had are terms of momentum. Okay. So I'll say the initial kinetic energy is equal to the final kinetic energy. So here I'll put the momentum initial of the nitrogen squared over 2 times the mass of the nitrogen equals the final momentum of the nitrogen squared divided by the mass of the nitrogen plus the final momentum of the unknown particle squared over 2 times the mass of the unknown particle. Well, yay. What I'm going to do is I think I'm going to substitute in to get rid of this one, the final momentum of the nitrogen. Okay. So right here, we see I'm going to use the bottom equation, and I can write, okay, I have the final momentum of the unknown particle times sine of phi divided by sine of theta. Okay. So, excuse me. So that is the momentum of the nitrogen, so I need to square that. And of course I need to divide by the mass of the nitrogen, M nitrogen. Of course I have the plus P final question mark squared over M question mark. And I fear I haven't left myself enough space, so let's just scoot this over a little bit. There we go. So that takes care of the right side of the equation. Let's go ahead and take a shot at the left side. We have 1 divided by the mass of the nitrogen. And I have an expression for the initial momentum here. It's right here. Excuse me. So what I'm going to do, what I'm going to do is I'm going to take this and substitute it in. And what I have is P final of the nitrogen cosine of theta plus the final momentum of the unknown particle cosine of phi squared. Okay. Now you notice, oh, wait a minute, now I've reintroduced that. Right, there's the final momentum of the nitrogen again. So I've got another substitution to make. So at the end of the day, I have 1 mass of the nitrogen. I have momentum of the unknown particle times sine of phi divided by sine of theta times cosine of theta plus the momentum final of the unknown particle cosine of phi, that whole thing squared, is equal to, of course, we have this, 1 over the mass of the nitrogen, momentum final of the unknown particle, sine of phi, all divided by sine of theta squared, plus the final momentum of the unknown particle over the mass of the unknown particle. And here we get to say goody goody. Notice that each one of these terms contains the momentum of the unknown particle squared. It's like magic. So what did we do? We substituted in to get rid of the initial momentum and the final momentum of the nitrogen particles. And then the momentum of the unknown mass also canceled out. So if I look at this bottom equation, yep, given that, given, everything's given except for that sucker, which is wicked awesome. So now all we need to do is get that final thingamadobob by itself. That's the technical term, by the way, the thingamadobob. Let's get the unknown mass all by itself. Excuse me. Well, yeah, let's go at it. So I'm going to take this and move it to the other side. Excuse me. I'm just going to take this and move it to the other side. So I have 1 over mass of the nitrogen times sine phi cosine theta divided by sine theta plus cosine phi, that whole rigmarole squared, minus, let's put this in parentheses, minus sine of phi divided by sine of theta. That quantity is squared. Equals 1 over m question mark. And that's technically it, right? We are done with what we actually need to do here. Okay? Now, of course, if we want to kind of, I guess if we wanted to actually simplify a little bit more, let's see, what can we do here? One of the nice things, if I pull a sine of theta out, okay, so this is technically it, that's all we need, but if we wanted to simplify this expression a little bit more, what I could do is I could do something like this. Sine of theta squared times, now we have sine of phi cosine of theta plus cosine of theta, cosine of phi sine of theta squared minus sine of phi over sine of theta squared equals 1 over m question mark. Of course, this, you'll notice, goody, that's an angle summation formula right there. This whole rigmarole can be expressed as sine of phi plus sine, got a little overzealous, sine of phi plus sine of theta. That's what this whole term in parentheses is. Which is pretty cool, right? I mean, now we can just express it as, if you notice, we basically have what is, I pulled this out, I have that as well. So I have 1 over the mass of the nitrogen sine squared of theta times the quantity sine of phi plus theta minus, that's squared, of course, minus sine of phi squared equals 1 over m question mark. So our last bit is just flip it, right? Take the reciprocal of both sides. I get m question mark equals the mass of the nitrogen sine squared of theta. That whole quantity needs to be divided by sine squared phi plus theta minus sine squared of phi. Pretty cool, huh? Wicked awesome. Yeah, I love it. Of course, yeah, go back, double check. I mean, there's a lot of algebra. I'll give you that. Okay? And in fact, this isn't the first time. I know from the video, it's like, oh yeah, I know exactly what I'm doing. No, I had to do it a couple times on the board. See? See, look at the whiteboard. I had to do it a couple times. Okay? It took me a couple times before I got it. Okay? Just in terms of simplifying it. I was actually here a couple times, but it was a matter of, okay, I knew there was a way to get it simpler than that. Okay. So the cool thing is that there's actually a bit of a restriction here. And we notice it's actually right here on the bottom. Generally, well, we refer, excuse me, we restrict our masses to be greater than 0. And because of that, we see that down here in the numerator, that sine squared of phi plus theta minus the sine squared of phi, that all must be greater than 0. Right? Or sine of phi plus theta must be greater than sine of phi. And here we have to be a little bit more careful. So let's go ahead and plot. Let's say, for example, you've got some line at an angle, oops, excuse me. Say you have something at an angle of phi. So if this is sine of phi, this represents sine of phi, that height, okay? Which means you've got to have an angle, if I keep the same length, okay, when you get to phi over here, okay, so that's when the height is the same. So think about taking this this length and rotating it, okay? So it'll rotate up and come back down. So the sine of phi right here, and this is the sine of phi right here. So theta can be any angle in between these two, right? Theta can cover whatever range this is. Okay? In other words, let's see, well, this angle right here between those two is 180 minus 2 phi. Right? Good. Yeah. So theta can be any angle, any value that's less than 180 minus 2 phi. Right. Good. So for example, let's say that phi is 60. If phi were equal to 60 degrees, okay, so 60 and 60, this would be 60, that means theta has to be less than 60 degrees itself. Okay? Or for example, if phi were 30 degrees, well, say theta would have to be less than 60 degrees. Okay? Or if phi were 30 degrees, okay, that would mean that theta would have to be less than 120 degrees. Et cetera, et cetera, et cetera. Well, that's kind of cool. It just makes sure that, for example, when I'm programming in, you can't just randomly pick values, right? You have to pick values that satisfy this internal condition here. I just can't randomly make it up, which I got to be careful about. So in any case, that actually takes care of the rest of the answer. I'll leave it at that for right now. It seems pretty cool, huh? Okay. Well, hey, thanks for your attention. I'll see you next time.